In this video, I want to talk about the topic of restricted Boltzmann machines. A restricted Boltzmann machine, which we are going to refer to as an RBM from now, is a generative stochastic artificial neural network that can learn a probability distribution over its set of inputs. So the main takeaway it said is a way to generatively model the distribution of the data. So it was initially invented in 1986, but it was mainly Geoffrey Hinton with his collaborators that invented fast learning algorithms for them in the mid-2000s. They have a variety of applications in dimensionality reduction, classification, collaborative filtering, feature learning, topic modeling, and many body quantum mechanics and many other applications such as, for example, label noise and things like that. And they can be trained in either supervised or unsupervised ways depending on the task. Now the term restricted refers to this specific structure that you have. So you have a set of visible units and a set of hidden units, and we're going to talk about them, but the main restriction here is this bipartite structure, meaning that in the visible units, the nodes are not interconnected, and the hidden units also follows the same structure. And we have two groups of unit, again, visible and hidden. This restricted structure allows for more efficient training algorithms, and it facilitates a easier structure for also the Gibbs sampling, which is a core component of training the robust Boltzmann machines. Specifically for gradient-based contrastive divergence and persistent contrastive divergence algorithms, this is very crucial. When we talk about the standard version of RBM, you have a binary valued hidden and visible units. You're going to have an m by n matrix of weights in which the element Wij is associated with the connection between the visible input Vi and the hidden unit Hj. And therefore, they define this energy function here, E via H, in which V is the visible nodes, H is the hidden nodes. And you have these two biases, and you have this W weight connecting the V's and H's. Thus, the joint probability is defined based on this energy function, like this. Therefore, for example, for the values that would make sense, you want this energy to go low in order for the probability of those to go high. One thing to again note is that given that restricted Boltzmann machine follows that bipartite graph structure, it's going to mean that if you, for example, look at the hidden units, they're mutually independent given the visible unit activations. Now, conversely, the visible unit activations are mutually independent given the hidden unit activations. It makes sampling easier, Meaning that, for example, the probability of V's conditioned on H would be the multiplication of the probabilities of each individual neuron conditioned on H. The same goes for the V as well. The items in the visible units of restricted Boltzmann machine can be multinomial, but the hidden units are usually binary values and follow the Bernoulli distribution. Now, for example, for the probability of Vik, again, it's a visible node, let's say for class K. If it's going to be a multinomial, if it's going to be a multi-class, it can be reduced to a softmax function instead. As for the training algorithm, the idea is to choose, for example, W such a way that for all of the visible examples, this probability of them is maximum, or the log probability of it has to be maximum. The idea is this. First of all, you're going to have to do Gibbs sampling, meaning that roughly speaking, you have some sort of a Markov chain sampling procedure in which you take a training sample, let's say V, you compute the probabilities of the hidden units, and then you sample the hidden unit H from this probability distribution. So it's like one step going from V to a hidden variables. Now, the idea is that in the Gibbs sampling, if you keep continuing undoing this, meaning that you compute the probability of V given this H now, sample the V again, and then compute the probability distribution of H, sample H again, and if you do this infinitely, you will end up with, let's say, a sampled V and H from the joint distribution of V and H. But it is shown that even one step actually works really well. So this is like a single step contrastive divergence algorithm. What this means is that you take the sample V again, you compute the probability space of the H, and you sample H from it. In some sense, let's say this is like your positive sample or positive example. And then you compute the outer product of V and H, you call this the positive gradient. You can see it here as well. And then now from H, you sample a reconstruction V prime of the visible units, again, using the distribution of these conditioned on this H that you have sampled. And then you also use this new V, let's say V prime, and resample the hidden activation H prime from this. And this is the single Gibbs sampling step for getting a H prime and V prime to constitute a negative example. And then you compute the outer product of V prime and H prime. This is going to be the negative gradient. Now, why are these called positive and negative gradient? Because in the procedure that you have for updating the W, you want to add this to W. Going back to the energy function, you know that this thing adds to the W. Now, in order for the probability of something based on that energy function, which has a term minus V transpose times W times H, the W for those, that term for those has to go up in order for the negation of it to go down, and therefore the exponent of that to go up. So you want to increase this W for the examples that are positive and decrease it for those that are negative. So if you can look at this here, this term is added to the W. So if you look at, for example, V and H, now you have this additional term which increases the W for this V and H. So for example, if you take this term alone, you multiply it by V from the left and H from the right, you will have a positive value added to it, therefore it adds to the probability of it being observed. And then for V prime and H prime, it is the other way around. So it decreases that, therefore reduces the probability. So if you look at the distributions, you basically want to take a V and H that would make sense. For example, let's say a picture from sci-fi or something, and a label, or the distributions of the H and V for that specific thing. And then you want the energy of that to go down in order for it to be kind of like, let's say, more stabilized, and for the probability of it to go up. And if you sample V prime and H prime, let's say you have like this random image and a H prime being, let's say, the label, you want that energy to go up because you don't want, let's say, noise to be associated with anything. And then you want to keep doing that in order for the model to learn to associate, let's say, low probability to the joint distribution of, let's say, a noise and something that resembles, let's say, a label. And therefore you do this, and the same thing goes for the A and B as well, because they get data, they have to do with the energy function as well. So with this scheme, you kind of modify the energy function through time. Now, this is contrastive divergence. If you keep the state of that Gibbs sampling, meaning that once you, let's say, obtain the final H prime, you keep that, and then you start from that in doing the Gibbs sampling for the next example, and then you go on and go on. That would resemble a long chain of Gibbs sampling. Now, that is called the persistent contrastive divergence, indicating the fact that the state of the Gibbs sampling is now persistent. And this concludes our video. And this concludes our short introductory video to restricted Boltzmann machines. Thank you.